Good afternoon, everyone. My name is Zhang, and I'm a postdoctor at the UCL Hawkins Institute. Today, I will present my research work on 3D acetabular surface reconstruction for cup prediction in total hip arthroplasty. Total hip arthroplasty is an effective procedure for for treating anesthesia hip arthritis. It mainly involves the procedure of replacing the hip joint with a prosthetic implant, and the number of primary THA has been rising dramatically worldwide. In THA, the precise acetabular cup size is critical as it influences the initial implant stability, long-term survivorship, and the restoration of hip joint kinematics. Both oversizing and downsizing will cause patient pain and follow-up surgeries, such as the revision surgery. Oversizing causes the bone fracture and impingement, and downsizing causes the poor implant fixation and failure. However, selecting the correct acetabular cup is challenging. Intraoperatively, the surgeon usually takes a try and error approach, which leads to incorrect size selection. To preoperatively determine the cup size, the surgeons use a 2D digital method, which is the golden standard in clinical practice. However, it only achieves a 70% accuracy. By contrast, CT scanning can achieve a higher accuracy and typically reserved for complicated cases, but it can incur the high cost and radiation exposure concerns. So, if 3D acetabular surface map can be reconstructed from X-rays, and it can assist the surgeon in determining the accurate cup, and also reduce the dependence on CT. So in this work, our objective is to reconstruct the 3D acetabular map from X-ray images, and the map can be used to estimate the cup size. This figure shows the proposed framework. As we can see, the input is 3 views of X-ray images, and also a standard hemispherical surface model. And the two main modules is the square root velocity function module, which is used to calculate the correspondences between the model projection contours and the acetabular rim contours on the X-ray images. And another module is the embedded deformation graph, which is used to manipulate the model shape. For the square root velocity function, it was defined as the curve's velocity divided by the square root of its speed. By using such a presentation, the 2D curve or 3D curve alignment problem can be formulated as an optimizing problem that is invariant to rotation, translation, and scale. So this module can provide very robust and accurate correspondences. Then, using the correspondences, the embedded deformation graph technique is used to iteratively deform the input model. Thus, the model projection contours can be aligned with the observation from the X-ray image. And so, in this paper, we consider the problem as an optimizing problem given multiple views of X-ray images and combining the square root velocity function and also embedded deformation. We use 3 terms. The first term is the rotation term, which is used to ensure the deformation is as rigid as possible. And the second term, which is a regularization term, which is used to ensure the deformation is as smooth as possible. And the last term is our proposed term, to ensure the alignment between the X-ray contours and the model projection contours are aligned. The proposed framework is validated by simulated and real patient dataset and compared against the SOTA methods. In the simulation, one AP view and two lateral views are generated from CT to test the robustness and accuracy of the proposed framework. We give noise to the observation and also give different noise to the rotation, translation, and scale of the input model. In the real clinical practice, we collect 5 groups of datasets, each include a CT scan, 3 view X-ray images, and the intraoperatively confirmed curve dimensions. The contour observations are annotated by 2 orthopedic surgeons independently to ensure the reliability. As this figure shows, this example of the simulation result on the 5th level noise. From the left figure, we can see there are large difference in the shape, scale, and also pose between the input model and the ground truth. After reconstruction, we can see from the middle figure, the reconstruction is well overlapped with the ground truth. And the right figure shows the error distribution. We can see most of the regions are reconstructed with a very low error, around 1 millimeter to 2 millimeters. Although some region we can see which is yellow, the error is around 3 millimeter, but this has less influence on the curve estimation. This figure shows the reconstruction error distribution using our proposed method and also compare methods with the increased noise level 1 to 5. We can see our method can achieve the highest accuracy. This demo shows the in vivo real data patient dataset impairment. As you can see, after 2 times of corresponding calculation, our method can get a very good reconstruction, as we can see from the bottom left. And also, we can see from the top right, the model progression contours are well aligned with the X-ray observation. So we put our reconstruction together with the CT model. We can see our reconstruction is well aligned. And the middle one shows error distribution. We can achieve error, mean absolute error around 1.3 millimeter. And the second demo shows the result on the 5th patient data. And our algorithm normally takes 1 to 3 times of correspondence calculation. And the algorithm can finish in around 2 minutes. And on the 5th patient data, we achieve 0.9 millimeter reconstruction error. Based on reconstruction map, the surgeon can use it to estimate the cup size. We compare the estimated cup size with the intraoperatively confirmed cup size. And we can get the mean absolute error and the standard deviation of the cup estimation is 1.3 millimeter and 1.2 millimeters. The estimation error stays within the half step of the standard implants in 4 millimeter increments. So this conclusion can support that our method can support the accurate cup size prediction preoperatively. To conclude the paper, in this work, we propose a novel 3D acetabular surface reconstruction method using minimal 3 views of X-ray images. And we validated the robustness and accuracy using simulation, and also validated the clinical feasibility using the real patient dataset. Thank you for your attention.